everyone, welcome to the course on electronic systems for cancer diagnosis. As the course intends us to teach more about biosensors, today we are going to study more about an important type of biosensor called an impedance biosensor. What do you mean by impedance biosensor? A sensor which is fabricated with an intention to measure the impedance parameters. What is the impedance parameter and from where does this come? So when we are talking about integrating a sensor and transducing the various physiological parameters of cells and tissues and understanding their mechanism with there could be alterations in their physiological parameters, and how do we leverage them and integrate that and understand, and all of this requires a biosensor which provides us a platform to understand the various physical parameters which we are intending to study based on based on the altering temperature or environment conditions. Now, one such example is, like I mentioned, a sensor which can measure the impedance parameters. So, it is already understood, the literature talks about various parameters like the change in pH, the change in temperature, oxygen consumption, the ion concentration, the cell membrane, the potential varies. The membrane potential can be measured depending on different environment where the cells are exposed to multiple challenges. So all of these parameters, like I mentioned, the different potential, pH and the impedance is another important parameter which is which also falls under these physiological parameters, which can be used to study these the alteration that happens in cells. It could be due to disease or it could be due to some biologic interaction. A kind of interaction is the protein-protein interaction, like the antibody, the antibiotic. Say there is this antibiotic susceptibility. So you have an antigen and an antibody. They are the two types of proteins. So when they interact, when they bind together, so not all combination, they're different, there are multiple sets of antigen and antibody, so not everybody bind. So when there is a right combination out of the n number of combination, when the right antigen and antibody combine, so this binding creates a difference in potential. So when the two bind, there is a change in impedance. This is how this parameter, the potential, which can be studied because of the binding, the change in impedance, which is a result of the right antigen antibody bind, is what is used in immunotherapy and antigen antibody, the antibiotic susceptibility test. All of these are multiple tests which are performed just to understand the right antigen and the antibody interaction. So what is the electrical parameter which can be used to understand the right interaction? Like I mentioned, it is the change in impedance. Now this impedance can be measured using a biosensor. Now what goes into the biosensor? How do we fabricate it, and how are these impedance parameters measured, the alterations studied, and how can they be characterized? All of this requires an instrument called the impedance analyzer. More into the details about the impedance analyzer will be explained by me shortly. So when we are talking about impedance analyzer, the instrument uses a 4-probe mechanism. What is a 4-probe mechanism? So when you want to measure something, say resistance across a given resistor, you just hold it, you have a multimeter, you hold the two leads and then measure the resistance. So you change the dial to where you can measure the resistance and then measure the resistance. Or you could change the voltage, you could change current, you could do multiple measuring with the help of two leads. But this is a 2-point mechanism. But when we are talking about 4-point, it is mainly used when we need highly precise readings, high precise measurements. there is a parameter called the contact resistance. So what happens is, when the let's say I take a multimeter now. So here we have a multimeter. Let's say I have a multimeter, and then you do the resistance measurement, and here you have two leads, this, the sensing and the ground. So you have these two leads to do the measurement. It could be the voltage measurement, the current measurement, you could do the resistance measurement. All of this can be done using the two probes. But when we see the contacts, the electrode, the tip here offers some resistance. This is a parasitic resistance. The point of contact between the lead and the electrode, the sensing, the point where the measurement has to be done. So these two create a resistance called the contact resistance. This could be of high importance when you are doing precise measurements. So the amount of resistance what the biosensor could measure, the impedance change, like one point which has to be considered even before you are doing the impedance is the cells what we are talking about. They are more insulating in nature. So in order to measure, so you need to apply some voltage and then flow the current. So there's not enough current that can flow through these. They are not good conductors like you can see a copper lead or like the aluminium or silver. They're good conductors and you could flow current and measure. But when it comes to biological cells and tissues, they're not really good conductors. So the amount of current that could flow through them is very minute. And in order to measure the impedance, so you need to apply some voltage and then measure the amount of current that flows through them. So all of this creates challenges. Now that the cells are not really good conductors, how do you flow them? Now, so it is already understood that you could apply some small voltage and then externally force current to flow through them and then do the impedance measurement. For that, this instrument cannot be used. Like I said, the amount of impedance what we would be measuring is really minute and it requires high precision and sensitivity, which an instrument like this cannot offer. And that is when we use the impedance analyzer, and it has, like I mentioned, it has 4 probes. The sensing elements are divided into 4. What happens when you divide them into 4 is, so the 2 electrodes are used specifically only to force voltage, and the remaining 2, the sensing electrodes are used, the sensing wires can be used only to measure the current. So now your voltage and current measurements are done by dividing the entire system into from 2 to 4. Now there is a drastic reduction. So the chances of eliminating the parasitic resistance which can be caused because of the contact between the electrodes and the surface can be eliminated. So this is where a 4-point probe or the 4-terminal sensing mechanism comes into picture. And let's see what are the different and how these 4-point probes can be used in order to measure the impedance of a biosensor. More about the details, let's get a hands on the instrument which is here. So this is the LCR meter, also called as the impedance analyzer. In our case, we are doing the impedance measurement. Otherwise, there are different parameters, like I mentioned, based on the type of chemistry, the changes in different parameters could be measured. So here, there is one example of a sensor. So this is the biosensor. So this is the biosensor in my hand, which measures the impedance. So we call it an impedance biosensor, and this is used to test the antibiotic susceptibility. So what happens is, how do you do the impedance test? Like you could see here, there are electrode pads. Each of these are electrodes, and when you force voltage on these electrodes and then measure the corresponding current, so this ratio of the applied sinusoidal voltage to the measured current gives you the impedance. So that is why we call this an impedance biosensor. This is a PDMS layer on top which has micro wells. So there are 3 devices here, and each of this micro well has interdigitated electrode. Why is the electrode? So when you load your sample, like I mentioned, the physiological parameters like the change in impedance when there is a binding between the antigen and the antibody can be leveraged through these electrodes which are inside each of these micro wells, and these electrodes are externally given connection here, and these are the electrode pads at the bottom where you could force voltage and measure the corresponding current, and hence we measure the impedance of the given sample. Now let's see how we could integrate this with the LCR meter or the impedance analyzer and do the test. So this is the LCR meter or the impedance analyzer. As you can see, like I mentioned, this is a 4 probe device, like the 4 terminal device. Here L force, L sense, H sense and H force. So each of these 2 channels here are to force the voltage, and the sense here are used to measure the current. So both source and sense, the entire mechanism is incorporated into these 4 channels coming out through the LCR meter here. The 2 probes. So these are the 4 leads. We have used a wire binding. So in order to make measurements using the impedance sensor which I mentioned, otherwise you could remove these external connection and then you can see the crocodile pins. So these are the 2 probes. Even before we start using, let's calibrate the device even before any measurement is taken. So initially, if you could see the display, there are multiple measurements. See the capacitance, L, inductance, reactance, susceptance, impedance, admittance. All of these parameters, depending on your application, can be measured. So when we are talking about AC circuits and when you are having sensors and you directly want to measure the admittance, so you could use this option and then do the measurements. Now we have it in the impedance mode. Let's say we want to calibrate. Open circuit trim here means open circuit calibration. So when I say OC trim, over what frequency range the calibration has to happen. We can select the different frequency range. You could choose all frequency. And now the 2 leads, the 2 electrodes in my hand are in open circuit configuration, and then we do the OC trim. Now that it is complete, let's do the short circuit trim. So this is the short circuit trim, and then I'll give it for all frequencies. So there's a throughout the so now it says failed because initially I did not hold it in a short circuit connection, so there was So initially there was an open circuit configuration. Now let me keep it in contact. Now that both of them are in contact, let's do now that it says the short circuit trim failed. Now that I have connected them correctly, let's do the short circuit trim and choose all frequency operation. Now both of them are in contact. And throughout the frequency range, the short circuit in a short circuit configuration, the calibration has been performed. So now that we have finished this, you could go to the measurement where you could measure for 10 millivolt. Say you could do the setting. So here you could use the option and then set the voltage which you want to force on the sensor and frequency. At what is the frequency sweep? This here is the 10 kilohertz. So you could choose the options for the applied voltage and the frequency setting. All of this once performed, let's see after calibrating the open circuit and short circuit, let's connect this to the impedance analyzer, the sensor which we have here, and do the measurement. Also, in order to give a proper, for the ease of performance, here there is the software which is linked to the impedance analyzer. So this is the software here connected to the PC. There are multiple options which are given here. Now let's say I stop. And then see this. You could choose the frequency, you could choose the voltage. Like I said, the force voltage is set to 10 millivolt. And then you could choose what is the measuring parameter. It could be the capacitance, inductance, reactance, admittance, or the DC resistance. In our case, let it be the impedance. And then we have the speed. So at what rate the measurement has to be performed. If you require the measurement has to be performed at a faster rate, you could choose fast. However, it could compromise on the accurate results which are obtained. So in order to get accurate results, keep it to medium, and then you could choose frequency or voltage, and then the start, the number of points where sampling has to be done, the start and the end frequency. These are the different options which are provided here. So let's see how we can plot the entire throughout the entire operating frequency range. Let's see the different impedance values that can be captured using the tool and the impedance analyzer system, which will be integrated with our biosensor. Like in one of the previous modules, I have already mentioned the use of a micro manipulator. So you could use the tool slot here to connect an indenter, like I mentioned earlier, if you want to study the tissue biomechanics, or in our case, now we have a biosensor which is placed here. So how do we, like I already showed you the different electrode placement. The external pads are very close to each other. Now, I'm sure you could even not see the numbering which is provided on this. So how do we manipulate this? Manually, there could cause a lot of errors and could even lead to damaging the sensor. So how do we precisely manipulate this micrometer variation in distance from one electrode to other? All of this can be easily handled with the help of the micromanipulator. In this case, we are using the micromanipulator and the sensing electrodes of the LCR meter. Let me connect each of this to the tool handle here. So now we've used the two manipulators and connected to the electrode pads of the third electrode. There are three devices like I mentioned. So the third micro well, which will be used now for experimenting. So I've used the 3 and 0 on the electrode pad terminals in order to connect to the manipulator. Now let's use the software to see the over the frequency sweep how do we measure the impedance of this. Now the well is empty, so just the paired resistance. Let's see what is the impedance that can be seen in the software. So initially we've taken care of doing the calibration, open circuit, short circuit calibration of the two sensing electrodes what we will be using for measurement. And once calibration is done, in the measurement phase after connection, let's see, so we'll have to connect to the COM port. And once the connection is established, we can see the different options. We've set the frequency level. So 10 millivolt is the applied voltage to the sensor. Now if we use the draw option here, now you could see how the readings are in progress. So over the given frequency starting from 20 Hertz, so there are 100, so here we mentioned 10 points. So starting from 20 to 100 Hertz, the 10 points where the frequency is being captured. This frequency is when the electrode, it's just the plain electrode with the sensor and the electrode pads. So the well has nothing in it, it's just empty. Now let's say I fill that with water. Here what I have is DI water. I would use a micro pipette. So this is a pipette here in my hand, and then let's use the so 100 microliter sample, 100 microliter of DI water is taken in this pipette. Now I would fill that in the third well. So in the third well goes the 100 microliter of DI water what I had taken. Now that the well is filled with water, let's do the frequency sweep and check the impedance measurement. As you see, there is a drastic change in the measurement here. So this was the empty well, and here so as you can see, this is the capacitance here. So we've changed the item which is measuring here is the capacitance. So we need the impedance measurement. So I'm going to stop the entire process. Again, change this. 10 millivolt is fine. So we need to do the impedance measurement and do the frequency sweep over this. So this is fine, 10 points, and then let me draw. This is showing 180 kilo ohm. The impedance is in kilo ohm with the DI water. So we've lost the readings because it was in the capacitance. The measurement was in capacitance mode. The empty well, the amount of impedance the empty well measured was not captured. But now we can see the impedance in kilo ohm. So it is dropping over the as the frequency increases. So this is with the DI water. Now I will take back the pull back the DI water which was put in the third micro well and then discard it. Here. And then let me take another pipette, and then now that we've used DI water, let's try using salt water. So 100 microliter of salt water is what I have in the pipette. Going to the third well. So here I fill the third well with salt water. Let's see what is the impedance. You could see there is a drastic drop in the impedance. Like we all know, salt water is a good electrolyte. You can see the difference in the resistance. So there over the given frequency there is a drastic drop in the impedance. So this was using the DI water. This green line here indicates the impedance measurement over this frequency from 20 Hz to 100 Hz. The impedance measurement of DI water, and this, the red what we see here, is the impedance over the given frequency range when you apply 10 microvolt across the two electrodes. So when you force 10 microvolts and across this frequency, you can see the amount of impedance, the difference in impedance what the DI water gives and the salt water gives. So this was a simple example. You could use the same experiment to perform the different antigen antibody analysis. The different tests can be performed using multiple samples and then study the cells, the physiology of the cells, and understand the electrical parameters like the impedance. And let me just discard the entire. So this is the Borosil tumbler which is used to discard all the pipettes which were used. So when you're talking about doing experiment with biology samples, always ensure you do not reuse them. That could be a major reason for contamination. So once that is discarded, so this is how the impedance biosensor is connected to each of the arm of the two arms of the micro manipulator, and the different electrode terminals can be connected, can be pointed using these manipulators, and this goes to the LCR meter where you can sense the voltage and measure the current with the other two leads. And like I already explained previously, the entire setup you can manipulate the movement using these arms on the control system of the micro manipulator, the Z, X and Y arms, and you could also choose the 1 and 2 option and then set the distance. So this we have just tested for the third well. There are multiple devices which are in the single chip here. All of these can be tested. For leak-proof, you could even calibrate each of these devices and then test the performance of each of the device which is on the single glass wafer. Now, let me just remove the salt water put in the third micro well and then discard it on. So this was a brief explanation about how to use a micro manipulator and the LCR meter. Like we mentioned, in order to measure the impedance, every time there is a bond, that is the antigen antibody, and when the two link, research says there is a change in impedance, and this phenomenon can be leveraged to understand the right combination of antigen and antibody and do the antibiotic susceptibility test, protein-protein interaction, and you could even do the immunotherapy, the multiple options. This was one such example where we used this device. If you can see the interdigitated electrodes, each of this, on top of each of these electrode is the micro well, where we loaded samples and the electrode pads externally, or where you force the 10 millivolt on these electrode pads using the LCR meter. So here you force the 10 millivolt on these electrode pads and then do the corresponding current measurement and do the impedance calculation for the entire set of electrodes. So now that we've seen how an impedance analyzer can be used, you could use them to do the various studies like the immunotherapy and other tests. I'm sure you understood how to operate, how the software can be used, and how different parameters can be changed, like the frequency sweep, the amount of voltage that you force in, the various parameters, electrical parameters that can be measured, the impedance, admittance, depending on the type of application. So this is how you could integrate a biosensor with the entire electronic system and then do the analysis. Thank you.